Right, we have 2 exam questions, so have a read through these and try your best to answer them, and then you can check your answers when you're ready. So the first one I would say is a reasonably challenging standard A-level question, and I'd say question 2 is certainly a star. I think that's quite challenging. So good luck with these. For question 1, I think one of the challenges is just getting all the information in the right place. Putting it all together correctly, and it's a little bit back to front in some ways, as we'll see. So we need to work out the resistance of the parallel section. So the R2, we don't know what that is, but we do know the resistance of the thermistor. So what we can do is apply the potential divider formula to this circuit. So we know the general form is V1 is equal to Vs multiplied by R1 divided by the total resistance. So possible confusion here with R1s and R2s, but if I apply this general formula to the circuit that we have here, the output voltage, the output PD, is equal to Vs, the total 12, multiplied by the resistance of this part, that's the parallel Rp, divided by the total resistance, which is R1 plus Rp. So we need to consider what is the resistance of the parallel section. So if we use this formula here, we can stick the numbers in. So we know that the output voltage is 8, the supply voltage is 12. Rp, we don't know. 250, 0.25 kilo, we know that value is R1 plus again Rp. So if you take 250 plus Rp in brackets from the bottom to the top, you can multiply that by 8, and we get 2000 plus 8 Rp is equal to 12 Rp. And then 8 Rp, take it to the other side, that becomes negative, so 4 Rp is equal to 2000, and we can find that the resistance of the parallel section is 500. But we're not there yet, we've still got to continue because we want to know the resistance of R2, and in parallel, R2 with the thermistor is 500. So we need to apply the formula for resistors in parallel. So 1 over R2 plus 1 over 650 is equal to the value we've just found, 500 if we invert the left-hand side. So invert 500 will give you 2 10 to the minus 3. Subtract 650 to the minus 1 will give you 4.6 10 to the minus 4, and then invert the answer. You get 2170 to 3 sig figs, or possibly a slightly different value if you've rounded up in a different way. So the answer to part A would be 2170 ohms. For part B, state and explain the effect on the output PD of increasing the temperature of the thermistor. So this is a bit more standard. We looked at some of these in the previous lesson. Top tip for exam tip, be very specific with your answers. A very common mistake for students here is to say something like increasing the temperature decreases the resistance. That will get you no marks because we haven't specified which component we're referring to. So be very specific. So increasing the temperature decreases the resistance of the thermistor. This will reduce the share of the voltage across the thermistor, as we've seen before, according to the potential divider formula. Therefore, the output PD will decrease. Question 2 is more difficult than it looks. At first glance, it looks like a pretty standard question, similar to what we've looked at in the previous lesson. However, it's a bit more complex than that, and this requires a deeper understanding of circuits. So a common mistake in here would be to say, well, yes, it does work, because as we've seen previously, as it gets dark, the resistance of the LDR will increase. Therefore, the share of the voltage across the section will increase, and that will turn the bulb on. Well, it won't do in this case, as we'll see, because we've got to consider, well, what are the values? And the values of the resistance R1 is very, very important, and also the resistance of the light bulb. So we could say, as the light intensity decreases, the resistance of the LDR increases. That is true. However, the maximum value that of the resistance of the parallel section is equal to the resistance of the light bulb. It cannot be larger than that. And this is due to this expression here. So if I think about the resistance of the parallel section, it's equal to 1 over the resistance of the bulb plus 1 over the resistance of the LDR, all inverted. So we can say, well, as the resistance of the LDR increases, then 1 over an increasingly large number will tend to 0. So this part of the expression here gets us close to 0, and it probably will be almost 0 because we're talking about mega ohms typically. So 1 over a million or 100 million is going to approximately be equal to 0. So then we're equal to 1 over R to the minus 1, which is equal to the resistance of the bulb. So the largest resistance that this section can take is 4.5. So if we work with that and then think, okay, well, what would be the share of the voltage of the 8 volts if the resistance of the parallel section is 4.5? And it's this value over here which is crucial. If R1 is 85, well, we can apply our potential divider formula. So 4.5 divided by the total resistance, 4.5 plus 85, multiplied by, that should be 8 volts, I think, not 6 volts. And we get 0.4 volts. So what we're saying here is that even when it's totally dark and the LDR has the largest resistance it possibly can, the resistance of the parallel section will tend towards the resistance of the bulb, which means the maximum value that the parallel section can take is 0.4 volts. And we're saying in the question that the PD across the bulb required to operate is 5 volts. The maximum we can get is 0.4 volts, so the circuit will not work. So really quite difficult. It almost seems to contradict what we've been saying previously, but it's not as simple as the voltage of the parallel section will always operate the device, as we alluded to last lesson. So we need to look at the numbers. In terms of an exam tip, always look at the marks in the question. So 4 marks would suggest this is a bit more difficult. So we need to really think about what's going on. Also think about why have they told us the particular values of 85 and 5 volts. So those are significant. If they hadn't told us those numbers, then we might be able to argue in general terms that this circuit would work. But depending on these values, in this case, then this bulb will not work.